Good afternoon, everyone. So, in this session, we'll be starting with the magnetism part one. So, whole magnetism will be in three parts. So, we'll be starting today in this session with the part one of the magnetism, right? We'll be discussing some of the important questions as well as PYQs, right? So, that will be discussed in this session, right? So, we'll be starting with the question number one. The question number one is with respect to the magnetic field, finding the magnetic field due to a current carrying wire, right? Due to a current carrying wire. We know that according to we use Biot-Savart law to find the magnetic field due to current carrying wires, right? So according to Biot-Savart law, the magnetic field due to a current element, that's TB, that's given as mu naught I TL sin theta upon 4 pi r square, right? Upon 4 pi r square. So this is the magnetic field due to current element, right? Where let's suppose this is the wire, right? And through this where the current I is flowing, right? Through this where the current I is flowing, then if we choose a current element dl vector, right? Dl vector, and we have to find the magnetic field at this point P. And now the line joining this current element and this point P will be this, right? This is the line joining this point P and the current element, right? Now the angle between this current element and the line joining the point at which we have to calculate the magnetic field, let's suppose that angle is theta here, right? That angle here is theta. So according to Biot-Savart law, this magnetic field due to this current element is mu naught I TL sin theta upon 4 pi r square, where r is the distance between the point at which we have to find the magnetic field and the current element dl, right? So this is how we can use the Biot-Savart law to find the magnetic field due to current element, right? And similarly, if we have a finite wire, right? If we have a finite length of wire, current I flowing through it, right? Then if we have to find the magnetic field at this, suppose at this point, right? This is the end A of this wire, this is the end B of this wire, right? So we'll join these two ends with this point A, joining these two points with point P, right? Point P. Point P is the point where we have to actually find the magnetic field, right? So at this point, we have to find the magnetic field, right? Let's suppose it's at a distance, point P is at a distance of, let's suppose T, right? T. Then one end of this wire is making an angle of phi 1 with respect to this point P, and another end of this wire is making angle phi 2, right? Then the magnetic field because of this finite wire will be nothing, that will be mu naught I upon 4 pi d, right? Mu naught I upon 4 pi d sine of phi 1 plus sine of phi 2, right? So this is the magnetic field that will be there because of this finite current carrying wire, right? So this is a very important equation, right, to remember, right, with respect to your exams, right? So for finite current carrying wire, the magnetic field at a given point P will be nothing. It is mu naught I upon 4 pi d sine of phi 1 plus sine of phi 2, where phi 1 is the angle made by point A with point P, right? And phi 2 is the angle subtended by the line joining the point P and the line joining the point P, right? So this is these are the two angles, phi 1 and phi 2, right? So this is the equation for the magnetic field because of the current carrying wire, finite current carrying wire, right? Now we can find out the current carrying magnetic field because of the infinite current carrying wire as well using the same equation, right? With the proper limits of this phi 1 and phi 2, right? You can see here, let's suppose this is infinite. The question one is says that find magnetic field due to infinite length wire at point P, right? So this is the point P here because of this infinite current carrying wire. Because of this infinite current carrying wire, we have to find the magnetic field at point P. Now you can see that this wire actually extends to plus infinity in the positive y direction, and it extends to minus infinity in the negative y direction, right? So that's the reason we say it as infinite length of wire, right? Now you can see here, the end of this wire will be at plus infinity, the lower end of this wire will be at minus infinity. It means that this point will make an angle of 90 degree with the upper end of this wire, and it will make 90 degree with the lower end of this wire as well. Or we can say, or we can conclude that phi 1 has to be equal to 90 degree and phi 2 also has to be equal to 90 degree, right? So phi 2 will also be equal to 90 degrees. So we can say that phi 1 and phi 2 are 90 degree each for an infinite current carrying wire, right? Now at point P at a distance of t, the magnetic field due to infinite current carrying wire will be mu naught I upon 4 pi d sine of 90 degree plus sine of 90 degree, right? So sine 90 is 1, so we'll be left with 2 times mu naught I upon 4 pi d, but that has to be equal to mu naught I upon 2 pi d, right? So this will be the net magnetic field because of this current, infinite current carrying wire at this point P, right? So mu naught I upon 2 pi d will be the current carrying, will be the magnetic field due to this infinite wire, right? So this is the main equation, right, that we'll be using for any current carrying wire to find out the magnetic field at a given point P, right? Now talking about the direction of this magnetic field, right, you can see here at this point, if we place the thumb along the direction of the current, if we place the thumb along the direction of the current, then at point P, the magnetic field will be into the plane of this paper, or we can represent that magnetic field with a cross, right? So at point P, the magnetic field will be at point P, the magnetic field will be into the plane of this paper, right? And the magnitude of this magnetic field will be mu naught I upon 2 pi d, right? And the magnitude of this magnetic field will be mu naught I upon 2 pi d. Magnetic field of this current carrying wire will be mu naught I upon 2 pi d. Now we have another question. Moving to the question number 2, find magnetic field due to given wire at point P, right? You can see here we have an infinite, semi-infinite current carrying wire, right? And there is a point P, there is a point P, there is a point P at a distance of D, right? There is a point P at a distance of D. And one end of this wire is making an angle. We can see the point L here. This is the lower end of this wire, right? It's making an angle of theta here, right? Angle of theta. And in the positive y direction, the wire tends to extends to plus infinity, or we can say it will make an angle of 90 degree with this point P in the positive y direction, right? So once again, we can apply the same equation. We know because of the current carrying wire, the magnetic field is mu naught I upon 4 pi d, right? Where d is the distance between the current carrying wire and the point P at which we have to find the magnetic field. Sine of phi 1 plus sine of phi 2, right? Sine of phi 1 plus sine of phi 2, right? Now you can see here the phi 1 angle here is 90 degree, and phi 2 here the angle is, it's making an angle of theta with the lower end of this wire, right? So the net magnetic field at this point will be mu naught I upon 4 pi d sine of 90 degree plus sine of theta, right? Sine of 90 degree plus sine of theta. So from here the net magnetic field will be mu naught I upon 4 pi d 1 plus sine of theta, right? 1 plus sine of theta. So this will be the net magnetic field. Now talking about the direction of this magnetic field at this point P. Now we have to place the thumb of our right hand along the direction of the current. Then the direction of our palm will give us the direction of the magnetic field at this point P. And it will be once again into the plane of this paper, right? Into the plane of this paper, and perpendicular to the plane will represent by a cross, right? Now, now you can see here in the question number 3, once again we have to find the magnetic field at point P, but the coordinates now at this point the coordinates of point P are given as 3, 4, right? And the current carrying wire is represented by this dot line, right? Dotted line. It means that the current carrying wire is perpendicular to the plane, xy plane here, and the current is coming out of this plane, right? And the current is coming out of this plane, and it is an infinite current carrying wire, right? Now we have to calculate the magnetic field at this point P. We know because of the infinite current carrying wire, the magnetic field is nothing. It's mu naught I upon 2 pi d, right? 2 pi d. This is the magnetic field at a distance of d from the wire, right? Uh, that's the magnitude of the current magnetic field due to current carrying wire. The current here is given as 25 amperes, right? Now the distance you can see here, the distance from this origin O, the distance from this origin O to this point P is given by this coordinate 3, 4, or we can say this distance from origin O to this point P will be nothing. It has to be D has to be equal to under root of 3 square plus 4 square, right? That's the distance formula, right? For any 2 points, the distance between any 2 points, you know that distance formula is nothing. It's that the distance between any 2 points whose coordinates are x2 and x1, right? That will be x2 minus x1 whole square plus y2 minus y1 whole square, right? This equation we have used to calculate the distance between the origin and the point P. So it will be under root of 3 square plus 4 square, that will be root of 25, right? So it means that the net distance between the origin of this Cartesian system to this point P will be 5, right? That will be equal to 5. So the magnetic field, the magnitude of this magnetic field will be mu naught I, the current here is given as 25 amperes, right? Upon 2 pi t, the distance comes out to be 5, right? This distance comes out to be 5. The value of mu naught is 4 pi into 10 to the power minus 7, right? Multiplied by 25, right? Upon 10 pi, right? Upon 10 pi. Now from here, pi and pi will get cancelled, right? So it will be 5 upon 2. That will be 2, right? 2 into 5 will be 10. So it will be 10 into 10 to the power minus 7. That will be equal to 10 to the power minus 6 Tesla, right? This will be the magnitude of the magnetic field because of this current carrying wire, which is perpendicular to this Cartesian XY plane, right? And the current is moving uh, through this plane, right? And out of this plane, we can say, right? So this will be the net. If we talk about the direction of this magnetic field at this point, right? The direction of this magnetic field at this point, it has to be along this direction using once again the right hand thumb rule, right? So this will be the net direction of this magnetic field having the magnitude equal to 10 to the power minus 6 Tesla, right? So this will be the net magnitude of the magnetic field at this point. Now let's discuss the question number 4. The question number 4 is that we have two parallel current carrying wires. Both the current carrying wires are of infinite length each, right? The current in first wire is 4 amperes and the current in the second wire is 6 amperes, right? There is a point P in between two wires, right? Point P is at a distance of 1 meter from the first wire and it is at a distance of 2 meter from the second wire, right? We have to find the net magnetic field, right? So it is nothing, if we calculate the magnetic field, direction of the magnetic field because of the first wire using the right hand thumb rule, because of the first wire, the direction of the magnetic field will be into the plane of this paper, right? And perpendicular to this point P, right? Similarly, the direction of this magnetic field because of this second current carrying wire, carrying current 6 amperes, it will be out of the plane of this paper, right? It will be out of the plane of this paper represented by this dot, right? Now the net, it means that the two magnetic fields at this point P are opposite in direction, right? So we'll subtract the two fields to calculate the net field at this point P, right? Let's first of all calculate the B1. It's the field because of first wire. That will be mu naught I upon 2 pi d, right? Mu naught I upon 2 pi d. That will be, let's write it in terms of mu naught only. Mu naught I, current is 4 amperes, right? And the distance is 1 for the first wire. So it will be 2 pi to 1. So we'll have 2 mu naught upon pi, right? This is the value of the P1. Similarly, the P2 magnetic field is mu naught I. The current here is 6 amperes upon 2 pi. The distance is 2 here, right? So it will be 3 mu naught upon 2 pi, right? 3 mu naught upon 2 pi, right? So the direction of this field is into the plane of this paper and the direction of this field is out of the plane of this paper, right? The net magnetic field B net will be, right? B net will be equal to, it will be B1 vector plus B2 vector, or that will be equal to 2 mu naught upon pi minus 3 mu naught upon 2 pi, right? So from here you can see here, so the net magnetic field here will be, it will be mu naught upon 2 pi, right? Mu naught upon 2 pi. This will be the net magnetic field. And the direction of this magnetic field will be given by the direction of this B1 field because the B1 is more in magnitude than B2. So the net direction will be into the plane of this paper represented by this cross symbol, right? So this is how we can find the magnetic field due to different configuration of the current carrying wires, right? Now let's, this is another question, similar question, right? You can see here, this symbol actually represents, it's a very important, if anywhere the symbol is represented by, let's suppose if there is a symbol represented by this cross, right? And carrying a current, let's suppose 2 amperes, right? And there is another symbol written by cross carrying a current of 3 amperes, right? It actually means that the current carrying wire is actually passing through this point perpendicular to this plane and the current is actually into the plane of this paper, right? Current is actually passing into the plane of this paper. In the same way, here it is present by a dot I and another current carrying wire carrying a current of 3I, which is passing into the plane of this paper, but the current is out of the plane of this paper, right? The current is out of the plane of this paper, right? So it means that if we find the direction, but we have to find the net magnetic field, the point where the net magnetic field is equal to zero, right? So it means that let's suppose there's some point P here, right, at a distance of x from this 5I, and the same point will be at a distance of 6 minus x from this 3I current, right? Now you can see here, because of both the current carrying wires, since the current carrying wires are having the same sense of the current, right, it means that because of the two wires here, in at any point in between the two wires, the magnetic direction of the magnetic field will be opposite to each other, right? Because the two parallel current carrying wires, right, at any point taken in between the two current carrying wires will have the direction of the magnetic field opposite to each other, right? So we can say that there is a possibility that in between these two current carrying wires, there may be a point where the magnetic field will be zero. We will try to find out that point, right? So because of this current carrying wire, the magnetic field will be mu naught I, the current is 5I, right? Upon 2 pi d, right? So the distance here is x, we'll write here is 2 pi x. So this has to be the current magnetic field equal to, because of this current carrying wire, that's mu naught I is given as 3I upon the distance, that's 2 pi. The distance here is 6 minus x, we'll write here as 6 minus x. Now you can see here there is no need to convert the centimeters into meters, because all the currents or the all other physical quantities involved will be cancelled out on both sides. So we need not to convert these distances into SI units, right? So we'll just cancel out this mu naught I, and mu naught I will get cancelled. 2 pi and 2 pi will get cancelled. We'll be left with 5 upon x. That has to be equal to 3 upon 6 minus x, right? Now from here, it will be 30 minus 5x. That will be equal to 3x, or we can say 30 will be equal to 8x, right? 8x. So the value of x at which the magnetic field comes out to be zero is nothing. It's 15 upon 4 centimeter, right? 15 upon 4 centimeter is the value of x at which the net magnetic field between the two current carrying wires, each carrying current of 5 and 3I, will be equal to 15 upon 4 centimeter, right? Now let's discuss about the magnetic field due to a circular coils, right? Magnetic field due to circular coils. Let's try to see what is the magnetic field due to circular coils first of all, right? Now you can see here, we can once again use the, let's suppose this is the this is the circular wire here, right? If this is the circular wire of radius R, right? And the current flowing through this wire is I. This is a circular wire of radius R, and the current flowing through this circular wire is I. We have to find the magnetic field due to this current carrying coil at this at the center of this coil, right? Now what we'll be doing here is that we'll be once again using the Bad-Savart law to find the magnetic field at the center of this coil, right? We know according to the Bad-Savart law, the magnetic field due to a current element is mu naught I dl sin theta, right? Mu naught I dl sin theta upon 4 pi r square, right? 4 pi r square, right? Where r is the distance between the current element and the point at which we have to find the magnetic field, right? Where theta is the angle between the current carrying element and the line joining the point where we have to find the magnetic field. Now you can see here we have to find the magnetic field at the center of this circle, right? Let's choose this as the current element. This is the dl vector, right? This is the current element, right? Now you can see here the direction of this dl vector is tangential to this circle, right? It's tangential to the circle, and we know in case of circles, radius is always perpendicular to the tangent, right? Radius is always perpendicular to the tangent. It means the angle between the current element and the point at which we have to calculate the magnetic field, it will be a 90-degree angle, right? So we can say here the theta here has to be 90 degree, right? Theta here has to be 90 degree. So I will get the value of B, that's dB, that's mu naught I TL upon, now the distance between the current element and the point here is R, that will be 4 pi capital R square, right? 4 pi capital R square. Now to calculate the total magnetic field because of the whole circle here, right, we'll have to integrate it on both sides, right? Now it will be B, this is the net magnetic field, that will be mu naught I upon 4 pi R square, right? mu naught I upon 4 pi r square integral of dl, right? Integral of dl. Now, integral of dl is nothing. It will give us the total length of the circle, or we can say circumference of the circle. That's 2 pi r, right? So it will be mu naught I upon 4 pi r square. That will be equal to 2 pi r, right? 2 pi r. From here, r and r will get cancelled, pi and pi will get cancelled, 2 and 2 will get cancelled. We'll be left with mu naught I upon 2r, right? So this is the net magnetic field because of the circular wire, right? Because of the circular wire carrying some current I, the magnetic field at the center of that circle is mu naught I upon 2r. Here I is the current flowing through the circle and r is the radius of that circle, right? Now we'll be using the same equation to solve this question number 6, right? You can see here two concentric circular coils of radius 5 centimeter and 10 centimeter are placed in a same plane, right? If current 0.2 ampere is flowing in both coils in same direction, then find the magnetic field at the center, right? So in both the circles, the current is flowing along the same sense, right? In the same direction, right? So the magnetic field at this point will be actually perpendicular to the plane of this paper and away from it, right? And it will be once again the same for this current carrying wire as well. It means that the two magnetic fields at the center will be along the same direction. The two magnetic fields at the center will be along the same direction, right? So they will eventually add up to give the resultant field at this point C, right? So net magnetic field will be, because of the first circle, right, smaller circle, that will be mu naught I. The current is 0.2 upon 2r. Now the r, the value of r is 5 centimeter. We'll write it as 5 upon 100 in meters. And then second magnetic field will be because of the larger coil, that will be 0.2 times mu naught upon 2r. The radius of the larger coil is given as 10 centimeter. That will be 0.1 meter, right? So this will be the net magnetic field, right? So it will be mu naught times it will be 100 multiplied by zero point 0.2, that will be 20 upon 10, right? 20 upon 10, right? So from here it will be 2, right? 2 and 2 will get cancelled. We'll be left with mu naught only, right? Mu naught. This and this will get cancelled. That will be 3 times mu naught, right? Now the value of mu naught is nothing. That's 4 pi into 10 to the power minus 7, right? So the net magnetic field here will be it will be 1.2 pi into 10 to the power minus 6 Tesla, right? This will be the net magnetic field at the center of this circle, right? So 1.2 pi into 10 to the power minus 6 Tesla will be the net magnetic field at the center of these two concentric circular coils, right? Now let's move on to the next question, and we'll also discuss about the magnetic field due to a circular arc at subtending an angle of alpha at its center, right? Now, first of all, we'll just try to solve this question. Two symmetrical current carrying rings are placed. There are two symmetrical current carrying rings. They are placed perpendicular to each other with common center, right? They are placed perpendicular to each other with common center. If magnetic field at the center due to one coil is P, then find the net magnetic field, right? Now you can see here there are two circular coils which are placed perpendicular to each other. It means that the planes of the two coils are perpendicular to each other, right? Having the current, they are symmetrical. It means that the current through this wire is same, right? Same current is flowing through them, right? Having the same radius, right? So the magnetic field, because of this wire, which is in the, now we can say YZ plane, the coil which is in the YZ plane, and there is another coil which is in XZ plane. So because of this wire, the magnetic field will be along this direction, right? It is in YZ plane. The direction of this magnetic field will be along X direction. We can write it as BI cap, right? BI cap. And similarly, the direction of the magnetic field, because of this coil, it is in XZ plane. It will be along positive Y direction, right? So then let's write that as PJ cap, right? PJ cap. And each of if magnetic field at the center due to one coil is P, so the magnitude of the magnetic field due to each of this coil is actually P. So the net magnetic field B will be equal to PI cap plus PJ cap, right? Or we can write mod of B will be nothing root 2 times P, right? So this is the net magnetic field at this point, right? And the direction of this net magnetic field will be along this direction. So this is the direction of the B net. So this is the direction of the net magnetic field, right? Now let's discuss the magnetic field due to a current carrying arc subtending an angle alpha at the center, right? Subtending an angle alpha at the center. It's a very important discussion, right? let's suppose this is an arc, it's subtending an angle alpha and the current flowing through this arc is I, right? It's subtending an angle alpha at the center. And let's suppose the radius of this arc is R and center is C, right? And current flowing through this arc is I, right? So the current through this arc is given as I. We have to find the magnetic field. We'll be once again using the Pvt law, right? Pvt law. Now the length element here is TL vector, right? TL vector. Let's suppose this length element subtends an angle of d theta here, right? Subtends an angle of d theta at the center, right? It subtends an angle of d theta at the center. So the net magnetic field at the center will be given with the Pvt law, that will be dB, that will be equal to mu naught I TL sine theta upon 4 pi r square. Now the distance between the current element and the center is capital R, that's the radius of this arc, that's 4 pi r square, right? Now theta once again here is 90-degree, right? We know that a tangent is always perpendicular to the radius in case of circles, right? So theta will be equal to 90-degree, right? So sine of 90 has to be equal to 1, right? That will be equal to 1. So dB will be here equal to mu naught I dl upon 4 pi r square, right? 4 pi r square. Now we know that this d theta is nothing. It's the arc upon the radius. It will be arc upon radius r. I can see that arc here, it's subtending the angle of d theta here. With the arc having the length dl, we can write d theta as dl upon r, right? dl upon r. Now we can replace dl here with r d theta, right? So dB here will be equal to mu naught I r d theta, right? Upon 4 pi r square. Now from here r and r will get cancelled, right? We'll integrate it on both sides, right? With the proper limits. Now the total angle subtended by this arc is alpha. So we'll integrate it from 0 to alpha, right? 0 to alpha. So it will be mu naught I times alpha upon 4 pi r. So this is the net magnetic field because of the circular arc subtending an angle of alpha at the center, right? So this is the net magnetic field, right? So this is an important equation. We can actually use this equation to find the magnetic field to two different arcs right at the center. So mu naught I alpha upon 4 pi r, right? Mu naught I alpha upon 4 pi r. Now we can check this also. Let's suppose for the complete circular wire, right? The alpha will be equal to 2 pi, right? We can substitute the value here equal to 2 pi for the complete wire, right? For the complete circle. So it will be mu naught I times 2 pi upon 4 pi r, right? So it should give us the same value, right? That we calculated here. That's mu naught I upon 2r, right? So it will be equal to mu naught I upon 2r, right? So it means that the result we calculated is the correct result, right? Mu naught I alpha upon 4 pi r. Now we can calculate for any angle, be it 30-degree, 60-degree, for quarter circle, for half circle, for uh, 3/4 of a circle, right? So such questions are frequently asked in your exams, right? So we must know all these equations to calculate the magnetic field because of such arcs, right? So this is one of the questions, right? Now you can see here in this question, we have to find the magnetic induction at the center O, right? The magnetic field has to be found at center O, at the common center O, right? For these two arcs, right? You can see here it's a quarter circle. This represents a quarter circle, right? Quarter circle. Or it is an arc subtending an angle of 90-degree at the center, right? So because of this quarter circle, the magnetic field will be mu naught I alpha, right? Alpha upon 4 pi r. Now, value of alpha here will be equal to, it will be pi by 2, right? So mu naught I pi upon 2 into 4 pi r, right? So from here we can say that the magnetic field because of quarter of a circle will be mu naught I upon 8r, right? So because of this quarter circle, the magnetic field is mu naught I upon 8r and it is into the plane of this paper and perpendicular to this plane, right? And similarly, magnetic field because of this quarter, three quarters of a circle, right? So if the magnetic field because of the one quarter is mu naught I upon 8r, then the magnetic field because of the three quarters has to be 3 mu naught I upon 8r, right? So it will be 3 mu naught I upon 8r, right? Now you can see here the net magnetic field because of this three quarters of a circle, it will be along the same direction once again into the plane of this paper. So the net magnetic field at the center will be P net, and the magnetic field because of these two small wires, right? It will be zero, right? Because of these two small wires, it will be zero because The angle between the center and the current element of these two wires is actually zero. So sine of zero is zero. So there will be no magnetic field contributed by these two line segments here, right? There will be no magnetic field contributed by these two line segments. So the B net here will be equal to, it will be mu naught I upon 8R. The radius of the bigger circle here is given as B, right? That will be mu naught I upon 8B and plus mu naught I upon 3 mu naught I upon 8A, right? So the net magnetic field here will be mu naught I upon 8 1 upon B plus 3 upon A, right? So this is the net magnetic field at the center, right? So this will be the net magnetic field at the center. Now discussing the question number 8. The question number 8 is that we have we have a semicircular coil as well as two semi-infinite wires, right? Arranged in this fashion, right? As shown in the figure, right? A long wire band as shown in the figure carries current I if the radius of the semicircular portion is A. Then find the magnetic induction at the center C, right? We have to find the magnetic induction at the center C, right? Net magnetic induction at the center C. So the net magnetic induction at center C will be because of the magnetic induction because of the three objects here, right? Because of this semi-infinite wire and this semi-infinite wire and because of this semicircular portion, right? For the semicircular portion, the magnetic field will be mu naught I alpha, right? Alpha upon 4 pi r, right? We'll be using this equation. And it will subtend an angle of pi at the center, right? So alpha here will be pi. So we will write here it mu naught I pi upon 4 pi r, right? 4 pi r. So pi and pi will get cancelled. We'll be left with mu naught I upon 4r. So this will be the net magnetic field because of the semicircular portion at the center, right? Mu naught I upon 4r. This is the net magnetic field, right? Now we have to find the magnetic direction of the magnetic field. The direction of the magnetic field because of this semicircular portion, it will be into the plane of this paper, or we can say cross, right? It will be in the cross direction, or we can say that it will be along the negative x direction, or we can say it will be along minus I cap, right? Minus I cap. So this will be the direction of the magnetic field because of this circular portion, right? And the direction of this magnetic field because of this semi-infinite wires will be along, we can use the right hand thumb rule, right? It will be along at this point C, it has to be along negative z direction, right? It has to be along negative z direction, or we can give the direction as minus k cap, right? For each of them, right? Minus k cap, right? And the magnitude because of the magnitude of magnetic field because of semi-infinite, that's nothing, that's mu naught I upon 4 pi d, right? Mu naught I upon 4 pi d, where d is the distance between the point and the wire at which we have to find the magnetic field. Now the distance here is a, that's the radius of the semicircular portion, right? So it will be equal to mu naught I upon 4 pi d, 4 pi a, right? Along minus k cap direction, right? Let me call this as b1, and b2 will be once again mu naught I upon 4 pi a minus k cap direction, right? Or we can say the net magnetic field because of this semi-infinite wires will be b3, that will be equal to twice mu naught I upon 4 pi a along minus k cap direction, right? So the total magnetic field here will be mu naught I upon 2 pi a minus k cap. Now there are two magnetic fields. One is this because of these two semi-infinite wire and because of this circular portion, right? And these two magnetic fields are perpendicular to each other, right? So the net magnetic field has to be equal to B net will be equal to under root of B3 square plus BC square, right? We can just plug in the value of P3 and PC in this equation to calculate the net magnetic field, right? Now let's discuss this question number 10, right? Question number 10. The question number 10 says that radius of a current carrying coil is R, the ratio of magnetic field at an axial point, which is 3r distance away from the center of the coil, to the magnetic field at the center of the coil. Now we know that the magnetic field due to the coil at its center is nothing. It's equal to BC, that's equal to mu naught I upon 2r, right? This is the magnetic field at the center of a coil, right? And let's suppose if there are n turns of the coils, then BC has to be n times, right? It will be mu naught Ni upon 2r, right? Now the question is that the ratio of the magnetic field at an axial point, which is 3r distance away from the center of the coil, to the magnetic field at the center of the coil, right? Now, at an axial point, at an axial point for this current carrying coil, right, of radius r, let's suppose this is the point P at which lies on the axial point. The magnetic field because of this point P at an axial point will be, that's given as mu naught I r square upon 2, right? That is r square plus x square to the power 3 by 2, right? To the power 3 by 2. So this is the net magnetic field at the axial point because of this current carrying loop. That's mu naught I r square upon 2 r square plus x square to the power 3 by 2, right? Now we have to find the ratio, right? We can just rewrite this equation. We can rewrite this equation. If we take r as a common from the denominator, we'll be left with 2, it will be 2r cube here, right? 2r cube, and we'll be left with 1 plus x square upon r square, right, to the power 3 by 2, to the power 3 by 2. Now from here r square and cube will get cancelled, we'll be left with mu naught I upon 2r. So mu naught I upon 2r is nothing, that's equal to bc, that's the magnetic field at the center, right? We can write b axial is equal to magnetic field at the center bc upon 1 plus x square upon r square to the power 3 by 2. 3 by 2. So from here we can find the ratio between B axial and the B center. So B axial upon B center will be equal to 1 upon 1 plus x square upon r square to the power 3 by 2, right? Now the value of x here is given as 3r, right? It's a 3r distance away, right? We can substitute the value of x here. So it will be 3r, that will be 9r square, and r square will get cancelled. We'll be left with 10 to the power 3 by 2. So this will be the ratio between the magnetic field at the axial point and the center, right? So this is an important equation. That's a relation between the magnetic field at the center and at axial point, right? So with the help of this equation, we can find out the ratio between the two magnetic fields at axial point and at the center of the current carrying wire, right? Now let's move on to the question number 11, right? The question number 11 is a solid cylindrical wire of radius r carries a current I. The ratio of magnetic fields at points which are located at r by 2 and 3r distance away from the axis of the wire, right? So we have to find a ratio of magnetic fields at points which are located at r by 2 and 3r distance away from the axis of the wire, right? Now you can see here, let's suppose we have a cylinder here. Let's suppose we have a cylinder here. This is the cylindrical current carrying wire, right? And this is, if this is the cylinder and there is some net current I flowing through this cylinder, right? Net current I flowing through the cylinder, and let's suppose the radius of the cylinder is r. Radius of the cylinder is r. So we have to find the magnetic field at the point which lies outside the cylinder. Let's suppose point P at a distance of r, right? And we also have to find the magnetic field inside the cylinder. So what we'll be doing here is that we'll be using the Ampere's second law, right? We can use the Ampere's second law for this portion, right? We can use the Ampere's second law for this point P, which lies outside this solid cylinder, right? And we know that all the calculations will be done on this Amperian loop, right? And the Ampere's second law is integral of P dot dl, that has to be equal to mu naught times the current enclosed by this Amperian loop, right? I can see here that current enclosed by this Amperian loop will be the total current flowing through this cylinder, right? The current enclosed by this Amperian loop will be the total current flowing through this cylinder. That's current I, right? And you can see, you also know that we also know that the nature of the magnetic field lines around this current carrying wire is actually circular, right? They are circular loops, right? It means that at each and every point, the direction of the B vector will be along the direction of the DL vector, or we can say the theta here between B and DL will be 0 degree and cos 0 is 1, or we can write here it as BDL, right? BDL, that will be equal to mu naught I, right? BDL, that will be mu naught I. And at each and every point on the Amperian loop, the magnitude of the magnetic field is a constant, right? The direction of the magnetic field is different, but the magnitude of the magnetic field at each and every point on the Amperian loop is a constant. So we can take B outside this integral, right? So it will be we'll be left with integral of dl, right? That will be mu naught I, right? Mu naught I. Now integral of dl is nothing, that will give us the that will give us the circumference of this Amperian loop, that's 2 pi r, that will be equal to mu naught I, right? So the magnetic field due to a slender current carrying cylinder outside the cylinder will be mu naught I upon 2 pi r, mu naught I upon 2 pi r. Or we can say here the magnetic field is inversely proportional to the distance from the center of the cylinder, right? For the outside point. So P is inversely proportional to R. Similarly, we can find the magnetic field for this cylinder for an inside point, right? For a point which lies inside the cylinder. Let's suppose there's a point P, there's a point P which is at a distance of let's suppose small r from the center, right? We have to find the magnetic field here, right? What we can do here is that we can draw an Amperian loop at this point, drawing an Amperian loop at this point, right? At a distance of r. Now, once again, the magnetic field at each and every point on this Amperian loop will be a constant, right? So we can use the Ampere's law, right? That's P dot dl will be equal to mu naught I enclosed, right? Mu naught I enclosed. Now the I enclosed will be the current enclosed by this Amperian loop which lies inside the cylinder. We know that it's the current carried by the cylinder is a uniform current, right? Uniform current density is flowing through it. Or we can say that the current density has to be a constant here, right? So current density will be I, that will be current divided by perpendicular area, that will be I upon pi r square, right? That has to be the current density of this Amperian loop as well. That will be I enclosed upon the area of this Amperian loop, that's pi r square, right? Pi and pi will get cancelled. So the current enclosed by this Amperian loop is nothing. That's I r square upon capital R square, right? So we can substitute the value of this I enclosed in this equation, right? To calculate the magnetic field. So integral of B dot dl will be nothing. It will be into 2 pi r, right? That will be mu naught I r square upon capital R square, right? From here, R and R will get cancelled. We'll be left with value of B inside, that will be equal to mu naught I into R upon 2 pi R square, right? So we concluded that the magnetic field because of the magnetic field because of the cylinder for an inside point is actually directly proportional to the distance from the center of the cylinder, right? Now if we plot the graph between the magnetic field because of the cylinder as a function of distance r, right? As a function of distance r. Let's suppose we plot this graph of a cylinder magnetic field for the cylinder as a distance of r, right? And we know for an inside point that magnetic field is proportional to the distance r, so it will be a straight line passing through the origin. So at this point, the magnetic field will be now a maximum, right? And the maximum value of the magnetic field will be mu naught I upon 2 pi r, right? It will be mu naught I upon 2 pi r, and the maximum value of the magnetic field is always, it will be on the surface of the cylinder, right? It will be on the surface of the cylinder, right? Then it will be varying as 1 by r. It means that it will show a like behavior like this, right? So B here is proportional to R and P here is inversely proportional to R, right? And here the value of magnetic field is maximum. That's at a point R equal to capital R, right? So this is the behavior or variation of the magnetic field due to a cylinder current carrying a cylinder, right? Now, but the question is that the ratio of magnetic fields at a point, where to find the ratio of the magnetic fields at a point uh, which are located at r by 2, that means inside the cylinder, and 3r, that means outside the cylinder, right? Outside the cylinder. We'll be calculating it for both and to calculate the ratio, right? So we'll first of all calculate the magnetic field outside, that will be B outside, that will be equal to mu naught I upon 2 pi r. Now the value of r here is 3r, right? It will be mu naught I upon 6 pi r, 6 pi r. And the magnetic field for an inside point will be equal to mu naught I r upon 2 pi r square, right? The value of r for the inside point is given as r by 2, right? It's r by 2. So it will be mu naught r into r by 2. That will be r by 4 by r square, right? So r and r will get cancelled, right? Now we have to calculate the ratio between them. So B inside and B outside will be mu naught I upon 4 pi r multiplied by 6 pi r upon mu naught I, right? So this and this will get cancelled. Pi r and pi r will get cancelled. We'll be left with the ratio as 3 upon 2. So this is the ratio P inside upon the P outside. For the magnetic field in a cylinder carrying a uniform current I, right? Carrying a constant current I, or we can say the current density of this current carrying cylinder is constant, right? So this is how we can use the Biot-Savart law to find out the magnetic field due to cylinder or due to current carrying wire or due to different objects, and we can use the Ampere's sector law as well to find the magnetic field due to different objects, right? So that's it for today. So we'll be discussing the rest second part of this magnetism in the next lecture. Till then, take care and goodbye.